Okay. Welcome everyone. This is Nicola Marzari. I'm a professor at EPFL and a laboratory head here at PSI. And together with Giovanni Pizzi and a group of people that will help with the hands-on on Monday and Wednesday, and another number of people that will help with the question and answer, we are going to offer this class in the next 4 lectures. Sorry, let me enable the captions. The goal here is to showcase the capabilities of electronic structural simulations, in particular having in mind the needs of the user communities at large-scale facilities. So the school really needs to provide a basic, what we call a gentle introduction, and make everyone understand what are the fundamental ideas behind quantum mechanical electronic structural simulation, and actually how to run the simulations. And Giovanni and the team have worked hard for the past couple of years to make sure that you could access this through very user-friendly web interface that launch reliable workflows that do the calculations that you need. As you know, all the material is going to be uploaded to our Indico PSI page. If you have registered, you'll also receive emails. So on Friday, tomorrow, you'll receive instruction on how to deploy the AIDA Lab interface. That is particularly relevant for those of you that are following us in remote, because for the PSI participants, we actually have a PSI instance set up here. And in the long term, everything will be persisted on our dissemination portal, the Materials Cloud, and in particular in the Learn section. And this is the structure of the class. So today we have a couple of hours. We have to finish actually 10 minutes earlier because there will be another event here at 4 o'clock. Today is mostly, hopefully gentle, still an introduction to quantum mechanical simulations and electronic structure theories.
There's an issue with sharing. We see this, so it's too big. So we can move it smaller. The rectangle.
Does everyone has this problem of seeing 2 slides?
Just make it smaller. That's fine. Try to change. Change slides. See if this works.
Let me try to enlarge it a little bit at least, so that Giovanni, is it still okay like this?
Yeah.
Cool. So thanks a lot, and please stop me if there is anything else. So the class is organized around these 4 lectures. Tomorrow we really see how these theories work in practice. That is how you can predict materials properties with the simulations. On Monday, we dig a bit deeper in actually what are the computational parameters and computational setup to do this simulation. And we start also these hands-on sessions on premises and in the cloud that everyone, both here and in remote, can follow. And in particular, in the last lectures, Giovanni and Tim will describe how this automated simulation can be very relevant for large-scale facilities. Okay, first thing, please ask questions at any time already now. If there is something that is not clear on the structure of the class, just raise your hand and I'll also repeat it from everyone at home. Okay? Cool. So electronic structure simulation means quantum mechanical simulations. And, these are the sort of four, I think, driving ideas on why they are relevant. We use them to understand, predict, and design molecules and materials. We will not see in these classes, but often, actually, they force us to develop novel ideas and microscopic and mesoscopic theories. Some of these go from the, say, Berry phase theory for the polarization and magnetization of solids to ideas in transport theories like the Wigner transport equation. Very relevant for this audience is that we use them to support, streamline, and inspire experimental efforts. And you'll just see one example. These days, they can actually push the entire process of discovery and innovation. So I decided to start with 5 or 6 visual examples to show you things that can be done. Some of these quite routinely, some of these, with some of the advanced capabilities that we have in the Laboratory of Material Simulation here in the Scientific Computing Theory and Data Center. So this is an example that comes from the Swiss watch industry. So what they wanted is understanding if we can predict the color of a material from first principle, and that really means calculating the reflectivity in the optical limiter, so understanding how a photon can excite an electron across bands or can excite plasmons. And if you are able to describe this faithfully, you can actually calculate how much light would be absorbed, how much light would be reflected, and thus the color and the shininess of the metal. And you see the results. I mean, so on the bottom, we have 3 experimental picture of osmium cesium and an intermetallic gold alloy. And what you see on top is the prediction without any input parameter. So the calculation doesn't know anything apart that you have pure osmium, pure cesium, or the intermetallic aluminum gold. But of course, once you are able to do this with calculations, if you want to try out a new material, it will take just the time of a calculation. You don't need to, source the elements to go into the crucible, get the material out, and then measure it. So it's a completely different, if you want, scalability in the cost of obtaining the result that you want, say a calculation on top versus an experiment on the bottom. A few other examples, this is the resistivity of a monolayer of graphene as a function of temperature and as a function of doping. And one can calculate what I say here, theory, is calculating the interaction between electrons and phonons, the vibrations, how they dissipate momentum, capturing that with, say, a coarse-grained Boltzmann transport equation and solving it accurately. And at the end, you not only, in this case, reproduce the experiments without any sort of fitting to the experiment just from first principle, but you can also understand what are the different microscopic mechanisms that make this happen. An applied example, working with a company, with Solvay, that has argyrodytes as a platform for their solid-state batteries. We could understand what are the dopants and co-dopants that are most favorable, so the energetics and thermodynamics of doping. And then for the different, in this case, chlorine and magnesium concentration, that were some of the optimal couples, we can identify the concentrations that lead to the maximum conductivity. And this is so relevant that then, the experimental groups at Solvay they do this in the lab, and they decide that, it's relevant enough that they want to patent it. It's also an example that I'll touch briefly tomorrow on how these days you can study very complex materials and very complex problems using machine learning, using neural network, that is training neural networks to reproduce the quantum mechanical results. And once you have trained them, you can actually access much larger length scale and much longer time scales. One area where we work a lot here is on spectroscopies, vibrational spectroscopies, infrared, Raman, X-ray spectroscopies, and so on. And this is just an example of, say, reactions at an electrified interface. And as a function of the potential, you see that there are certain species that appear. You see these vibrational peaks that appear. And you can actually explore what could be all the different adsorbates, in this case on these copper surfaces, and they have their own vibrational fingerprints. And so you can translate the experimental peaks that you see on the left into microscopic pictures that come from the right. Couple of more examples. As I said, the capability of doing reliable and predictive calculation are bringing us to the world also of material discovery. This is an example that comes from 2018 and then finished in 2023 of doing what Kostya Novoselov and Andrei Gaim did for graphene. They scotch tape graphite in a monolayer of graphene. And so with Giovanni and others in the group, we decide to scotch tape everything that is known. Do you know how many inorganic stoichiometric materials we know? Exactly. So depends on how you count and everything, but I would say on the order of 80 to 100,000. So this is our portfolio of materials for application, and we scotch taped all of them. It took 5 million CPU hours. That is not that much these days, and that at the time was equivalent to spending 40,000 francs. And we were able to discover graphene. Suddenly it was already discovered, but we have discovered 2,000 easily exfoliable materials that can be scotch taped and that we are exploring for many different applications. And sometimes you also stumble on the unexpected. Indeed, if you look at all these inorganic stoichiometric compounds and you look at their primitive cells and the number of atoms that sit in the primitive cell, you discover, and these are these pink histograms, that having a number of atoms that is a multiple of 4 is very common. And I'm sure that any of you now think, so I have an explanation for that. And we have thought hard for a year at finding an explanation, and we actually couldn't. We have explored everything. And actually, just to give you a sense, it's not really the high symmetry space group that are mostly bringing this, we call it rule of 4, multiple of 4s in the primitive unit cell, but is the low symmetry space groups. And so sometimes you also discover something completely unexpected. Okay, this was the hors d'oeuvre, the sort of introduction to giving you the sense of the capabilities, with the understanding that especially here, we work to develop capabilities that are relevant to PSI or that are relevant for large-scale facilities across the world. One more sort of set of thoughts before we start the actual lecture. I told you already when we were talking about the gold alloys that the model is different. Actually, it was in 2019, I gave a talk on this topic to a room like this, but everyone was a billionaire. It was at Jim Simon's house in New York. And, I was terribly worried that people would fall asleep because these are all stock market kind of guys. And so I told them 100% returns every 16, 18 months, and everyone sort of was, wildly awake. But this is what has been happening with regular digital computing. Basically, we have had, every 16 to 18 months, a doubling of capacity. So it means that a calculation that took 1 year in 1993, when I started my PhD, these days I would take 3 seconds. So I could do my PhD in 9 to 12 seconds, basically. That is very satisfactory. And this is just with digital capabilities. Maybe there will be also quantum computers, but certainly what there is very powerfully these days is machine learning and artificial intelligence. And I'll comment a little bit tomorrow on this. And, you know, in order to exploit this enormous, you know, availability of computing power, you really want theories that are computable. That is, you want theories that give you equations that can be implemented on a computer. And this is why something that, you know, we'll discuss extensively today, that is density functional theory, has become so popular because it's very computer friendly and the prediction that it gives you are very accurate. And actually Walter Kohn, that was the person behind it, got the Nobel Prize in 1998. And, you know, they're computable not only on, you know, the supercomputers that we have here in Lugano or across the world, but, and this is probably my finest accomplishment, you can use a cell phone. This is from 2010, is my Nokia Linux cell phone, where I installed everything, linear algebra, fast Fourier transform, and in 45 seconds, it calculates the ground state of silicon. And this was 2010, so it wasn't, you know, even remotely close to the power that cell phones have these days. And that also means that this kind of simulations these days are really prevalent, not only in universities, not only in research laboratories, but in companies. You'll see tomorrow how much Google and Meta and Microsoft are investing in this field. Last time I did the statistics in physics is actually 2019. These were the journals of the American Physical Society, and looking at the most cited papers. And the one in red are on electronic structure simulations. So apart from, you know, graphene and photonics, everything else, you know, was massively, you know, driven by all this, especially density functional theory calculation, not only in physics and materials, but all over. So Nature, more than 10 years ago, looked at the most cited papers in the entire history of our scientific literature. They went back to the 18th century, covering all fields, not only science, but medicines, biology, engineering. And then they analyzed the top 100 papers and the top 10. And actually the most prevalent field was indeed the density functional theory, with 12 papers in the top 100 and 2 papers in the top 10. So I call that, you know, the most relevant and the least known scientific theory of the 20th century. It's so present in, you know, a lot of the work that is being done, and actually, you know, so little known outside of the community. And, you know, I use today to give you a little bit of a flavor of this, and then we'll see it in news. Okay, so we're going to start now with the actual class. Are there any questions before we start? One thing that is important, we have a team of people, including Nicola Colonna, Yuri Timrov, and Edward Lescott here in the room. That, you know, Nicola, Yuri, and Edward are actually at PSI, so they are your point of contact. And I think there are also some people in remote. They will monitor the question and answer pane. So this is very relevant for those of you that are online. If you have a question, you can type it on the question and answers. And as soon as it's answered, both the question and the answer will become public. So use the question and answer. The chat is blocked to avoid giving you nefarious inspirations to sort of disrupt the lecture, but the question and answer can be used and is monitored. So what we'll really do today is understanding how we can use quantum mechanics to give us the accuracy that we need. How many of you feel fresh about your quantum mechanics? Let's do a show of hands. 1, 1.5. Okay, very good. So I'm going to teach you quantum mechanics in 10 minutes. Okay, so this is so this should be light-hearted enough. Starting, I mean, I guess I could have had the shortest PhD thesis in those 12 seconds, but this is the shortest PhD thesis I know of, and this is de Broglie in the 1910s, writing a 12 pages, I think, PhD thesis that basically postulated this fundamental, I say, equality. And what it says is that any object in the world, from the moon, an elephant, a golf ball, a virus, an atom, an electron, will have a certain momentum P, okay, mass time velocity. So if your velocity is large or your mass is large, you have a lot of momentum. And depending on the momentum that you have, you will also have a wave-like character that is described by a wavelength lambda. And the wavelength lambda is defined by this equation where h is a Planck constant, and it's very small. It's 6.6 10 to the minus 34 joule. So the net result of this is that if you put my mass and my velocity, my wavelength is infinitesimal. So I look pretty sharp to you, okay? I don't sort of delocalize around. And as we go smaller and smaller and smaller, the mass becomes smaller and smaller and smaller. But even when we are at the mass of the proton, the wavelength remains very small. It's only when we go from the proton to the electron, there is a factor of 2000, 1800 in the mass, that all of a sudden the wavelength of the electron starts to be of the order of angstroms. And so the wavelength of the electron starts to be comparable with the typical length of the space where the electron lives. And the net result is that electrons do behave wave-like under almost all circumstances, and we can't study them anymore as classical objects, but we need to study them as a wave-like object, while mostly everything else, even the very light proton, behaves almost classically, so behaves like a tennis ball, say, shot by Federer. And, this is an example what it means being wave-like. If I take, say, an electron and I shoot it towards a barrier that has a double opening, a bit like the Young double slit, actually the wave that represents the electrons, you see, diffracts, refracts back, and the diffracted piece of the wave interfere with each other. You see the two opening acts almost as point-like sources, and the wave after the opening shows a diffraction between these two sources. And that's why at the end, quantum mechanics is computationally complex, because you don't have to study anymore point-like object, but you have to study waves and how they evolve. Point-like objects are simple. For those of you that believe that, we sent people to the moon in 1969, we could integrate the equation of motions, Newton equation of motion, on the computers of the time, on the first solid-state computers. It took much longer to be able to solve quantum mechanics in realistic days. So de Broglie decides which object is quantum and which object is non-quantum. For the non-quantum, for the classical objects, Newton had given us the equation of motion, F equal mass time acceleration, to understand how we can send a rocket to the moon. To understand what is the equation that drives electron, we needed to wait December 27, 1925. Do you know what happened on December 27 of 1925? Schrödinger went skiing. So he went skiing every Christmas, and he would go to Arosa. Schrödinger had a colorful life, so I can't tell you all the details here because we are recorded, so look them up on his biography. But he disappears in Arosa with the mysterious lady of Arosa, and to me it's never clear who did the work, because Schrödinger, after the equation, didn't do much. But on the 27th of December, he writes this. I think this is translated. I suppose he was writing in German, really. But, you know, says, I'm very optimistic about this thing, a new atomic theory, and if I can only solve it, it will be very beautiful. And that allows us to say that quantum mechanics was invented in Switzerland. And not only quantum mechanics, but also special relativity was invented in Switzerland. So this is 1925. And 4 years later, let me actually show you the equation. This is pretty scary. We'll try to understand what is this equation, but this is the equivalent of Newton's equation for a particle. The only thing is that now we have a wave. So this is describing just one electron. And so it says that as all waves, at every instant in time and at every point in space, we have an amplitude. And the equation that this wave amplitude psi needs to describe, it's a little bit complex. Let's not dive into the detail, but involves the second derivatives. It involves multiplying by the typically Coulomb potential. Maybe, you know, we are studying the hydrogen atom and there is a proton that attracts the electron. So this V is the Coulombic attraction of the proton, and the derivative in time of the wave function. How did he come up with this is actually not so unimaginable. It came from somehow optics and the principle of least action, but I'll show you in a moment how you can understand this in a very simple form. But let's say 1925, Schrödinger equation, great excitement. So all of a sudden, the entire community worldwide is energized. And, 4 years later, Paul Dirac, that was also half Swiss and half British, writes this famous statement that says, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are those completely known, are thus completely known. And so the only challenge is actually solving this equation because the exact solution is actually too complicated. And I highlighted in red the British speak of Dirac, that, he was actually saying here that chemistry is quite easy and physics is a bit difficult. So, Schrödinger equation explains all of chemistry and a large part of physics. So 1929, and then in 1963, so 34 years later, there is an addendum from Dirac that says, if there is no complete agreement, one should not allow oneself to be too discouraged. And it's very interesting because in 1964, Walter Kohn took a sabbatical to Paris from San Diego, and that's where he developed the first theorem of density functional theory that I would say revolutionized computational quantum mechanics. So, the complexity I told you of quantum mechanics is really in the amount of information that you need to deal with. So if you want to describe one tennis ball, you just need to give position and velocity, so 6 numbers in 3 dimensions. And then you can do everything. We can send the Voyager deep space probes, billion of kilometers away from here. If instead you want to describe, one single wave, you need to give the amplitude. Think of this as being the c, so the height above the sea level, everywhere in space and at every instant in time. And actually, it's a little bit more complex because the Schrödinger equation has also an, say, imaginary part. So we are actually working not with classical water waves that would have real amplitude, but with waves that have amplitude that is a complex number. And, just to show you how complex this is, I'm going to take a very simple example of an iron atom. Iron is the heaviest of the common elements in star, say, nucleogenesis. And so an iron atom has 26 protons. So there is a charge of 26 in atomic units on the nucleus that keeps together these 26 electrons. And sadly, the wave function of 26 electron is a function of the electron number 1, electron number 2, electron number 26. And in 3 dimensions, this means that this is a function of 78 variables. Okay. And a function of 78 variables is impossible to manage. Okay. Because even if you were, say, to do a very simple coarse sampling, you take a little cube and you divide it into 10 slices in each direction, as Hartree, that was a computational chemistry in Cambridge, says, you know, if we need you know, the value of psi, where R1x can have 10 possibilities, you know, this and this and this and this and this. R2x, 10 possibility, R3x, 10 possibility, and so on. Then R1y, R2y, R3y, R1z, and so on. We are going to have 10 to the 78 numbers. So 10 to the 78 numbers is more than the numbers of atoms in the universe. Okay. So even an extremely rudimentary sampling of the wave function of one single atom is beyond our capabilities. And so we need to scratch our head and do something better. And we'll see how we scratch our head. And we start actually looking a little bit more deeply into this Schrödinger equation, starting from the Schrödinger equation for one electron. And in particular, we are going to make an important but quite accurate approximation. That is, we are going to say that the potential in which these electrons live is actually independent from time. So in the iron atom, we had 26 protons and neutrons, so that, you know, inside the nucleus is very small. The nucleus is 10 to the minus 15 meters. So for our purposes, it's point-like, and there are these 26 electrons around, and we are making the approximation that the nucleus doesn't. In reality, the nucleus moves. Say you have a piece of real iron, it's, you know, there is thermal agitation, but the electrons are so light, and we'll discuss this later, and the nucleus is so heavy that even when it moves at glacial speed. So it doesn't really matter. It moves so slowly from the point of the view of the electrons that it seems almost frozen in time. So let's make this approximation. The potential V, typically the Coulombic attraction from the nucleus of the atom, from the nuclei of the molecule, from the infinite set of nuclei in a silicon crystal, is independent of time. So the solution of the Schrödinger equation can be decomposed in a space part, in a time part. It's what you do with differential equation. You do separation of variables. You can write the wave function psi of RT in a slightly cursive psi that depends only on R times a function f that depends only on t. And so when you do that, rather than having one differential equation, what I shown you before when Schrödinger was in Arosa, you end up having two differential equations, but one is just in space and the other one is just in time. And the blue one just in time is trivial to solve because the derivative of a function giving the function itself is the exponential. So we can always solve that part. And that part actually cancels out when we calculate equilibrium properties, and you'll see it later, but for those of you that have some memory, if we calculate expectation values, we will have the exponential on the left and the complex conjugate of the exponential on the right, and these two give rise to one, they are complex exponential. So let's actually forget about this, okay? It would be relevant if you start driving an atom with a free electron laser, but you know, who has a free electron laser. And so, you know, sometimes we actually have to use it. The space-dependent part is now a bit simpler than what you had seen before, and is what we have to solve. And basically what is saying this equation is that we need to have a wave function psi such that del square is the Laplacian, is the second derivative. You know, that this symbol just means the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. So we are saying that the curvature of the wave function psi at every point in space multiplied by this constant minus h bar square. H is the Planck constant, h bar is the Planck constant divided by 2 pi, m is the mass of the electron, but in any case, no, there is a constant minus something in front of the Laplacian, but we take the curvature of the wave function plus the product of the Coulomb potential times the wave function. So the sum of these two operations, second derivative on the wave function plus potential times the wave function, needs to give me a number times the wave function. This is an eigenvalue equation, okay? There is an operator in square parentheses, so we operate on psi, we take its second derivative, we multiply, but the result of doing del square and v, so the result of this operator in square brackets, is just stretching the wave function by a number e, okay, a constant times. So when we solve this equation, this eigenvalue equation, we obtain the wave function psi, and we obtain this eigenvalue E. And this eigenvalue E is actually the energy of the electron, or often one of the possible energy of the electron. There is typically a spectrum where the electron can take different values. Sometimes these different values are quantized. You know, in a hydrogen atom, the ground state would be at an energy that is -1 Rydberg, or, you know, -13.6 electron volt. And then there are excited states for those electrons, and they're all eigenstates and eigenvalues of this equation. If you take a piece of solid like silicon, there is going to be a continuum of states that can have certain energies, but there are also forbidden energy gaps where you can't have an electronic state. If you have now, you know, an impurity in silicon, you might create states where you want, like when you dope silicon with donors or acceptors, or you might have states that you don't want. If your silicon gets contaminated with gold, all your optoelectronic properties go haywire. Okay, so solving this for one electron is still easy. So you can do it analytically if you have a hydrogen atom. The proton is just a spherical potential -1/r. And if you know your Laguerre polynomials, because you're living in the 19th century and you're going to a French school, and you know all of these things, you spend 5 days and you solve. Already, if you have 2 electrons like the helium atom, you are stuck. You can't do anything analytically. And so the question is really, how can we deal problems of a real complexity? Actually, from now on, most often I will use this compact notation for my time-independent problem, and in particular for what is called the stationary Schrödinger equation here, stationary Schrödinger. So just the space-dependent part, and what is in the parentheses that I called it an operator, I actually call it properly a Hamiltonian, and so we say the action of the Hamiltonian operator, so we usually use a hat, sorry for the arrow, the action of the operator on psi is just giving you a number times psi. So we'll use this compact notation from where it goes on. And let me show you intuitively, actually, how this Schrödinger equation came about, because we can do an analogy between classical mechanics and quantum mechanics. So if you have classical mechanic quantities, and the typical one would be the total energy. Kinetic energy, that is the square of the momentum divided twice the mass, plus the potential. You can transform this, we call it physical observable, in this case, the total energy, into a quantum mechanical equation using this very simple rule. The momentum is transformed into a gradient operator minus I h bar, the gradient, and the position is just a multiplicative operator. And so if you transform the total energy, kinetic plus potential, p squared over 2m plus v, using these two rules, the term p squared over 2m becomes minus I twice, so I squared, so minus 1, h bar twice, so minus h bar square over 2m times del square. And so this is, exactly the correspondence from classical to quantum. What was a classical observable become a quantum mechanical kinetic energy operator. What was a classical observable, here the potential energy, becomes a multiplicative operator. So if someone had told you this, you could have invented quantum mechanics. Okay? I told you already, in all of this, we are supposing that the potential is static, is not moving. In reality, all the potentials that are all the nuclei in your system are moving, but what happens is that they are moving so slowly that it doesn't really matter. I had a postdoc in Boston that loved this analogy that is very appropriate for here, of the cow with the flies. And the cow is the massive nucleus, and the fly are the light electron. So the cows can't get rid of the flies by running fast. The flies are so nimble, so light, that even if the cow starts moving, one fly will still keep hovering on top of his head or on top of his tail. And there are technicalities on how we call it. Often people use the term Born-Oppenheimer approximation. Oppenheimer is the guy from the movie that liked to make atomic bombs. Sometimes it's called adiabatic. They have slightly different meanings, but let's not focus on it. But let's just say, in general, it's very true, except in the cases where it's not true. And those cases are a bit rarer, but let me give you a few examples where the adiabatic approximation breaks down. Suppose you are depositing an atom A on a metal surface M. So this is, what happens a lot in different deposition techniques. And here there is a very sophisticated movie that shows the atom being deposited on the surface. So you see this. What I see is actually this. That is, as a function of the distance of the atom from the surface, the atom is going to feel a certain force and is going to have a certain energy. Okay, so your system has an energy that, if you want, if you were to do it very, very slowly, so if your atom were to go very slowly close to the metal surface, it would follow this red curve. So it would always be in the condition of being at every distance in the minimum energy state possible, and at the end, it would stop here somewhere on top of the surface, in the most favorable configuration ever. But there are, and we call this the potential energy surface, that is the energy on which the atom moves. But there are a few other possibilities, that is, as the atom comes close to the metal, if the metal has a low work function, the atom, maybe it's quite electronegative, maybe it's a chlorine or a fluorine atom, it can harpoon an electron out of the metal. The metal has a low work function, so it's easy to get electrons out. It's a piece of aluminum, and chlorine is arriving, so this is aluminum, this is me chlorine. When I start to be close, actually, it's called harpoon. I suck an electron out, and so all of a sudden, I am in a completely different electronic configurations that I could call M plus A minus. So I removed an electron from the metal. I've become, say, chlorine minus. The metal has lost an electron, so it's slightly positively charged. And actually, the electron that has been lost by the metal means that there is an empty hole over there, and maybe that hole can be filled by another electron that sits on the metal but a higher energy, and then maybe this electron hole pair can combine, emitting a photon. So a lot of weird things can happen if you do this, and depending on the speed of the atom, you can have that the harpooning takes place earlier or later. So while if we were very slow, we would follow the red curve. If you start to be faster, we might actually follow sort of a combination of the different curves. And in these cases, what we are seeing are non-adiabatic effects. So the trajectory of the nuclei doesn't have always the electron at the ground state. It has electrons that find themselves all of a sudden in an excited state, out of which they can decay or emit light. Let me give you a couple of other examples. Something very relevant. If you look at the vibrations of, a very easy to measure optical mode in graphene. So everyone knows to do Raman scattering on graphene, and you dope it. Actually, what you have is that the frequency change in so this is 0 means, what we have at 0 doping. That is, if that is the relevant frequency of I think this would be the A1 mode. I've forgotten. It's probably 1500 centimeters to the -1. I don't remember the number. But as we start doping, if we consider the electrons at equilibrium, we would have that this would be the change in frequency of that optical mode as a function of doping. But in reality, the electrons in graphene at the Fermi energy are very sluggish. It's a little bit like, you remember the two crossing of the graphene band structure. It's a bit like filling a martini glass, and you shake these band structures during the vibration, and the electrons follow very slowly. And so you actually have the true change in frequency needs to take into account the fact that the electron now don't follow instantaneously the cow. So they are sort of, a bit slower. But this is very important if you're trying to understand, your level of doping in your nano device with Raman scattering. You need to understand how things change. So these two were examples, and then we'll stop on this exception of violations of the adiabatic approximation. There are other things that we are not considering, and we are not considering the nuclei as having a relevant wavelength. I told you, remember, de Broglie, lambda times p equal to h, so the wavelength of the nuclei is negligible. But if you go towards very, very light nuclei, like just one proton in a water molecule, actually there is a little bit of a quantum character from the proton, and it means that when the proton moves around in water, it actually tunnels like a wave, and it doesn't hop like a particle. And so the barriers are quite different, and the quantum is the correct barrier for the proton to go from one molecule to the other. That is actually much lower than the barrier that you would have if the proton couldn't tunnel. One example that I love is strontium titanate, so a perovskite. And you're all familiar with perovskites. You know, we have oxygen cages, titanium at the center, 6 oxygen around, the filler cations, the strontium. And what you have is that this material, as you lower the temperature, like all the ferroelectric perovskites, should go into a ferroelectric state. Okay, you take barium titanate, you know, at high temperature, it's paraelectric and cubic. You lower it, goes tetragonal, orthorhombic, rhombohedral, or you know, lead titanate, it goes directly tetragonal and stays. And if we were to treat all the nuclei as classical, this is what you would have. As you decrease the temperature, you have a first order phase transition, and your order parameter, you know, becomes different from 0, and you have a ferroelectric. But strontium titanate is not ferroelectric, even at very, very low temperature. And why is it? Is because a combination, the oxygens are fairly light, and the barrier, you know, in the ferroelectric state, you would have the titanium and the oxygen case that have off-centered themselves. And so you have 6 possibilities. You can have center like this, like this, like this, like this, like this, like this. But the barrier is shallow, the oxygen is light enough, and actually this entire oxygen cage quantum mechanically tunnels all the time across the 6 possibilities. And so it never locks itself in one of the 6, as it would do if it were classical and the material would be ferroelectric, but it keeps tunneling. And so the material is always cubic and is what is called a quantum paraelectric. So this is an example, or a couple of examples, where the wave-like nature of the nuclei can be relevant. But at the end of the day, both this and the Born-Oppenheimer violation are somehow rare and specific. There is one last quantum effect that instead is very, very important, and has to do with the fact that the nuclei are indistinguishable. Okay, I cannot, you know, label. If let's suppose I'm compressing. Maybe let's make it simple. Let's say I compress hydrogen. Okay, so if I compress hydrogen, what I have is that the thermodynamics of hydrogen reflects the fact that the nuclei are indistinguishable. I have a very good example that I actually teach in class. Suppose that you are the hydrogens, and suppose this is the container, and I start squeezing. And there is another element that I also need the temperature, no? So I'm squeezing, there is temperature. Temperature means that there is a little bit of electrical current under your chairs. And so basically in the ground state, you keep hopping because there are all these electrical discharges. So you are hopping because of temperature. I'm compressing you. And the pressure on the container is all the hits that you give with your head on the walls trying to escape. So you're there moving, hitting. And now what is important quantum mechanically is that if 2 of you are distinguishable or 2 of you are indistinguishable, so if 2 of you are classical nuclei, distinguishable, I can see the difference between the 2 of you. Or if 2 of you are quantum, that is undistinguishable, the kind of motion that you can do is different, because a motion where the two of you swap is a valid move if you're classical, because you are a different thing and you exchange your chairs while being electrocuted. While if you are identical, nothing has happened. That means that the thermodynamic and thermomechanic properties of, say, a gas of atoms are going to be different if I consider them, distinguishable or indistinguishable. And the same thing for other properties that are related to this, like how vibrations of a solid affect, again, thermodynamic properties like expansion or like specific heat. What is the specific heat? Specific heat is how much, heat a solid is able to absorb. If the nuclei are classical, there is a continuum of vibration. A nucleus can vibrate very little or a lot, and it's a continuum. And if instead a nucleus is quantum mechanical, it can only have discrete quanta of excitation, exactly as the quantum electron in a hydrogen atom has discrete quanta of excitation. And so, you take your glass of water, actually at room temperature, the vibrational modes of the oxygen hydrogen can never be excited, because those modes have frequencies of 3,000 centimeters to the -1, and room temperature is an average of 200 centimeters to the -1. So if you start to zap your water glass, at most you can excite very low energy modes like the rotational modes. No? That's what happens in a microwave. You warm up the water because you make it rotate. And so the specific heat of a solid at very low temperature is 0. A piece of matter cannot absorb heat when you start warming it up from absolute 0 because there is an energy. I hear voices. So there is an energy gap between the ground state and the excited state. And this is super important if you do material science, if you want to understand how your piece of diamond expands or contracts with temperature, you need to take into account quantum effects in the nuclei that don't really have to do with being delocalized, as we were saying before, but have just to do with being indistinguishable rather than distinguishable. Okay. Any questions up to now? So as I mentioned, people can write the questions in the question and answers. Is anyone writing questions in the question and answer? Sort of.
One question.
Fantastic. No, I mean, you answer it because, you answer it on the question and answers page. As I said, we have to finish 10 minutes earlier, so I'm not going to do a break for today. Tomorrow we'll do a break so you can breathe a little bit. And now we actually are going to dive in on what happens when you have a real system. For simplicity, we like water, we'll just keep a molecule of water. And so what do you have? You have one proton here, one proton here, one oxygen here. The oxygen brings, 8 electrons, 2 core electrons, 6 valence electrons. The 2 protons bring 1 electron each. So all of a sudden I have, a little bank account of 10 electrons, 2 protons, and an oxygen nucleus. And I'm going to mix all of this together and see what happens. And for every position of the 2 protons and of the nucleus, I can solve that Schrödinger equation. And then I can move the protons and the nucleus, and maybe I solve it again, and maybe I find an energy that is lower. And actually, the equilibrium geometry of the molecule is going to be the one where the hydrogen and the oxygen are roughly 1 angstrom apart, and the two hydrogens that are positive, you could imagine that they want to repel and the molecule is linear, but in reality, the way the electrons arrange themselves also makes them want to sit at a tetrahedral angle of 109 degrees. So what is the equilibrium configuration of your water molecule corresponds to the lowest energy possible for this collection of electrons and atoms. And what is the energy of this collection of electrons and atoms is the one given by the Schrödinger equation, where the operator, the Hamiltonian H, is this thing here that I'll describe, and this Hamiltonian applied to the electronic wave function gives me the energy of the electrons, and we are going to minimize it with respect not only to the electron-electron interaction, but also to, say, the nucleus-nucleus repulsion. And so, you know, what are the main players in determining this energetics of these 10 electrons, 2 protons, and 1 oxygen is the curvature of the wave function. So the second derivative, it's what we call the quantum kinetic energy, what used to be minus h bar over 2m del square. And now we have gone into what are called atomic units that are very convenient. So h bar equal to 1 in atomic units, mass equal to 1 in atomic units. So minus h bar square over 2m becomes minus 1/2. And the quantum kinetic energy is the Laplacian with respect to electron 1 plus the Laplacian with respect to electron 2, and so on and so forth. And so it's this object here. And then the 10 electrons are all attracted to the nucleus. So we have 10 electrons, and they want to be close to the first hydrogen, they want to be close to the second hydrogen, they want to be closer to the oxygen. And so that's the glue in some ways, you know, the Coulombic attraction is just that, you know, if the problem was classical, the, you know, hydrogens, I mean, maybe it's simpler to think at an atom. So if the iron atom was classical, all the electrons would want to sit on the iron nucleus. But this is not what the solution of the Schrödinger equation does. And in part, we won't go into that. It reflects what is called the indetermination principle. If all the electrons were to fall on the nucleus, their position and momentum would be perfectly known, and that goes against one of the laws of quantum mechanics. So in some ways, if you are a wave, you always want to be a little bit delocalized. So in the players, I was saying, in the energetics of this water molecule are the curvature of the wave function, the attraction of the electron to the nuclei, the repulsion of the electron with themselves. So these 10 electrons hate each other, so they want to be as far away from each other as possible. This is the third term, and these are all wave-like terms. And then there are, if we for a moment, you know, keep all the nuclei as classical, there is just a, say, if the nuclei are moving, they have a kinetic energy, p square over 2m, or if you are at equilibrium, this term is 0, and then the nuclei hate each other, okay? So it's a delicate balance. It's like living in a condominium. You know, there are people that you like, people that you hate, and you sort of all try to find an equilibrium. But this is what we have to solve, this quantum mechanical operator, for, you know, a realistic system. And the question, how are we going to do that? And to sort of introduce you a little bit to the problem, I'll actually use some very nice compact notation for calculating all the properties that I want. That was first introduced by Dirac, the guy of the whole of chemistry and a large part of physics, and is what is called the bracket notation. And Dirac, say, writes a wave function here in this symbolic form, what we call a ket, and he writes the complex conjugate of the wave function as a bra. There is something quite subtle in this that, we are talking about objects that are dual in the appropriate space, but we don't have to worry about this. What we have to, look at it are properties like the scalar products. So this electronic wave function, a little bit like vectors in real space, they live in a space that, might have many more than 3 dimensions, but you can still calculate a scalar product. And the scalar product is nothing else than the integral of the complex conjugate of one wave function times the other wave function. And we say that 2 wave functions are orthogonal, exactly as 2 vectors are orthogonal in real space if their scalar product is 0. Okay. And we say that 2 wave function, or say a wave function, is normalized if the scalar product with itself, so the scalar product of itself would be, let's say, psi r complex conjugate times psi I, so it would be equal to the integral of the norm. If the integral of the norm is equal to 1, this wave function is normalized. And now that you're expert with the Schrödinger equation, you see that if we take the, say, Hamiltonian operator and we apply to a wave function that is an eigenstate of that operator, applying what we have in square parentheses to psi gives me a number times psi. And so if I take the operator, I apply psi, and then I integrate psi star times this object, what I get is the integral of psi star times E times psi. E is a constant, so I get E times the integral of psi star psi. And if my object is normalized, that integral is equal to 1. And so what I get from this is actually the value of the energy of this electron. So this Dirac bracket between the wave function, the operator, and the wave function itself gives me in this case, the operator is the Hamiltonian, gives me the energy of that particle. So we call it an expectation value. Okay, with this, how do we solve, real system? How do we solve the water molecule that is really difficult? We use a lot what we call the variational principle. I won't prove it, but it's super easy to prove. That is, we can construct what is called an energy functional. This is a very important concept. So this is an energy functional. That means it takes a function as input and it gives you a number. A standard function is an object that takes a variable as input and gives you a number. So if your function is x cubed, so if x is equal to 3, you obtain as a result 27. Here instead we have something that takes a function as input and gives you a number. And so if I feed to this functional a certain psi, what the function is going to calculate is the expectation value psi h psi. So it's going to calculate the integral of psi star action of h on psi, is going to divide it by psi square, and the result is just a number. And what one can prove very easily is that you can feed to the beast anything. All the psi that you feed are going to give you different numbers, but these different numbers are always going to be greater or equal than the ground state energy. So if you were able to solve a difficult Schrödinger equation, you would be able to find the lowest energy eigenvalue, the first excited state, and so on. So you would be able to find E0. In general, it's very difficult, but what you can do very simple is feed the beast a lot of different psi, and then take the minimum energy that you have gotten from all these trials, and that's your best estimate for the ground state energy. Of course, if what you provide to the functional are very odd choices, your estimate is going to be very poor. But in reality, what you can do, we won't go into that, you can feed to the functional parametric function. So you don't feed it x cube, but you feed it a times x plus b times x squared plus c times x3 and so on. And so you can have a result that depends on a, b, and c, and then you minimize with a, b, and c. And there is a corollary to the variational principle that says that if we happen to have a psi that gives me exactly the ground state energy, then that psi is the ground state wave function, and vice versa. But I want to use it just to show you the three fundamental steps that have been made in quantum mechanics that were, the Hartree equation, the Hartree-Fock equation, and the density functional theory equation that are actually all very similar to themselves. And I'll start from the Hartree because it's really very inspirational. And, let's stick with iron for a moment. You remember what Hartree had said, that he invented the Hartree equation. He said, even if we do a pathetic job of, sampling space, with 10 position in all direction, we still need 10 to the 78 variables. Yeah. And what Hartree does is says, well, let's make an approximation in which, if you want, we write this wave function of 26 electron as the product of 26 functions. Okay? So the psi is now written as a function that depends only on electron 1 times a function that depends only on electron 2 times a function that depends only on electron 26. So here we had 10 to the 78 complex number. How many numbers we have on the right instead? Well, we need to describe phi 1 with the same accuracy, but this is just in 3 dimensions. So you have 10 numbers times 10 numbers times 10 number. So this is, 1,000 complex number. And then phi 2 requires 1,000 complex number, and so on and so forth. So now, in this Hartree approximation, I can describe an approximate wave function for my 26 electrons with just 26,000 numbers. So it's a, enormous simplification from 10 to the 78 to 26,000. And okay, so we don't know if this is a good approximation. What Hartree said, Hartree, is there anyone German here? Probably. So Hartree had become very good at the differential equation because during World War I, he needed to predict where bombs would go from England to Germany. And those are, it's a little bit more complex than Newton's equation of motion because you have friction, but Hartree had become very good at integral differential equation, trying to send all the bombs. And so the only good result of World War I is that we had Hartree being able to do this kind of math. And the kind of math that Hartree asked himself is, what are the conditions that phi 1, phi 2, phi 26 need to satisfy? And the conditions that they need to satisfy is that the 26 single particle, we call them wave functions, needs to be such that the energy functional is minimum, okay? Because the minimum of the energy functional gives you the, your best guess. And so this thing here, this minimum condition, are actually 26 differential equations. So we have gone from one differential equation, the Schrödinger equation, for 26 electrons, maddeningly complex to solve, to 26 equations, but now much simpler to solve and very intuitive, because they look all the same. All these 26 equations look the same, and they look almost like a Schrödinger equation. So I haven't done the math. It's a couple of pages of hardcore functional analysis, but it's not impossible. And the Hartley equation tell me that what each of these phi 1, phi 2, phi 26 need to satisfy is a Schrödinger-like equation where for each electron you have a quantum kinetic energy term. For each electron you have an attraction to the nuclei. Capital R is the position of the nuclei. If we have only, say, an iron nucleus in position 0, that Ri is 0, so just the Coulombic attractions to the nucleus. And then what is saying is that for each electron I, what this Hartree operator is telling me is that each electron I feels a positive term that is the sum over all the other electrons, so the sum over J different from I, of the square modulus of the J wave function integrated but divided by the distance. This is very intuitive because this object here, the square modulus, is nothing else than the density distribution of electron J. It's really the probability of finding the electron J somewhere. So where that square modulus is high, we have a high probability of finding electron J at that position or J. When it's low, we have got a low probability. And so high probability of finding an electron or low probability of finding an electron means that on average, the electron has a charge density distribution that is given by the modulus of a phi square. And then this is really electrostatic. If we have a charge density distribution, let's call this Nj of R, the electrostatic repulsion from that charge density distribution, and in particular the electrostatic potential given by that charge density distribution, means that we sweep all space. That's the integral in Rj. At every point in space, we have a certain charge density, and depending if you are, U electron Ri are nearby or far away, there will be a 1 over the distance term. So to put it differently, again, suppose you are the 26 electrons of iron, and the disk here is the nucleus. What this equation is telling you is that for each of you, what matters is your second derivative, your curvature. That's the first term. The second term is your Coulombic attraction to the disk. And then the last term is the repulsion that each of you feels for each other. You are all negative, so you hate each other. You want to be separated. And the true Schrödinger equation would have everything instantaneously aware of everyone else. So if you down there in the corner wave, you will feel him waving. And instead, the Hartree equations say we don't really look instantaneously at what happens. What we are looking is at the average distribution, maybe during the time of these lectures. So if I take each of you and I integrate you over the 2 hours of these lectures, you become a blob, sort of on average, you sit on the chair, but your average doesn't have to respond anymore instantaneously. And so what I'm saying is I start solving the equation for U, taking the repulsion from the average of everyone else. And then I study U, and I take the average repulsion from everyone else. So I solve these 26 equations. And, I need to start from somewhere. So I don't know what, you are. And maybe I say you are a sphere. Each of you is a sphere. So each of you has a charge density that is spherical. And I start solving this 26 equation. And, for you in the field of the other 25 spheres, I find that you become an ellipsoid. And each of you becomes maybe a slightly different ellipsoid. And then I iterate this equation in which now each of you on average is not a sphere, but is an ellipsoid. And I solve this equation once more. And now I get that you're not only an ellipsoid, but you're an ellipsoid with little handles. And I keep iterating this equation until I get to what is called self-consistency. That is extremely important. So I found a fixed point of my 26 equation. That means for each of you, I have your own wave function. If I take the square modulus of each of you, I have your charge density. And if I solve for one of you in the repulsive field of the other 25 charge density, I obtain again what I had at the iteration before. So I sort of, gotten to a condition where if I keep iterating, I don't change the solution anymore. I've reached self-consistency, and physically, what each of you is responding to is what is called a mean field solution. So we have transformed a very complex problem where everyone is feeling everyone. In the real Schrödinger equation, as I said, you wave, you feel it. So we have transformed this problem where everyone feels everyone else, that is impossible to solve, in a problem in which everyone feels the average of everyone else. This is the concept of mean field. You do this to solve the stock market. There are all these agents, and you can't really solve a problem with many agents doing their own thing. And so you transform each agent on the average of what it does. It's an approximation, but it can be remarkably, remarkably good. And this is what Hartree did. And as I said, what we have is, instead of one super complete equation, we have 26 much simpler equation. They need to be solved self-consistently. And we call an independent particle model because really, each of you just feels the average of the others. And what, Hartree would have done would have been this iterative procedure. As I said, first I say you're all spheres, you construct those integrals, you solve the equation. With the new solution, you construct again the average repulsion, and you iterate it until it converges. I mean, this is great in general. And so Hartree wanted to solve a real problem. And so he needed a calculator. And it was 1926, so he went onto the internet and there were no calculators on sale because they had not been invented. So he went to MIT, actually, where a lot of smart engineers are. And the guy here is Vannevar Bush, no relation with the family of presidents, super smart guy that had built a mechanical computer. So it's called a differential analyzer. And Hartree went and he was able to solve the Hartree equation for interesting problems. There was one thing that went wrong, but before sort of going into this, I need to do 2 minutes of a detour of Vannevar Bush, of which I am a fan, in particular because he wrote this in 1945. You see, he thought about a possible future in which man-made machines will start to think. 1945, 80 years ago. And he actually described, what he thinks will be the machines of the future. And he says, this machine will perform complex arithmetical computations at exceedingly high speeds. And this mathematics will be effective in bringing the growing knowledge of atomistic, the Schrödinger equation, to the useful solution of advanced problems of chemistry, metallurgy, and biology. And he called this machine a memex. And he said, in this device, you would be able to store all your books, all your records, all your communications. And now, sort of, with the technology of the time, he said, well, this has to be large. It's a desk, actually. And there are a lot of screens. And they didn't have televisions, no? So they are just projecting sort of transparencies. And there is a keyboard and a set of buttons and levers. And you see, it says there will be new form of encyclopedia ready-made with a mesh of associative trail. So you can point to a word and it will send you to what that relevant word is in the encyclopedia and so on. And it says that the poor chemist here will have all the chemical literature before him in his laboratory, and he will be able with these trails or hyperlinks to follow all the analogies of compounds and side trails to the physical and chemical behavior. So this is quite great, I would say, 1945, Vannevar Bush. So Hartree, used the differential analyzer, solved the problem, and went back to Cambridge. So this gives me also the chance to say, I think that, at least a few weeks ago, I don't know how is it going now, both Microsoft and Apple were more than $3 trillion capitalization. And I'm sure they have hundreds of thousands of engineers that try to figure out how to connect an iPad to a laptop. And it's one of the Schrödinger equation is easy. Just getting these things to work is very difficult. So what Hartree had missed in his brilliant idea was one fundamental laws of quantum mechanics that is called the spin statistics connection. This is almost mystical, and it has to do with indistinguishability. We have said, quantum mechanical particles cannot be distinguished. And that very weird concept has very practical consequences. When I squeeze you and I electrocute you, the head knocks on the doors are different if you're distinguishable or indistinguishable. And it's not only that, but we divide the world into fermions from Enrico Fermi, that was Italian, and bosons from Natyendra Bose, that was Bengali or almost Bangladeshi. Actually, he was the department head of the University of Dhaka for many, many years. And what the spin statistics connection is something very profound on the symmetry properties of the many-body wave function. If you have electrons, electrons have an intrinsic property that is the spin, and that spin is a semi-integer. So it means that they are fermions, and fermions need to satisfy this antisymmetry principle that if you take a fermionic wave function and you swap two coordinates, you need to get a minus sign. The square modulus of the wave function is not going to change, and the brackets are not going to change, because if you swap, you've got a minus that cancels out. But the Hartree wave function, let me write it here for, say, two particles. So for two particles, Hartree would have said that psi of R1, R2 is going to be equal to the product of a function f of R1 and a function g of R2. You swap R1 and R2, the function changes, so it doesn't satisfy a fundamental law of nature. What can you do to impose antisymmetry to the Hartree hypothesis? It's very simple. So rather than taking FR1 times GR2, you take FR1 times GR2 minus FR2 GR1. You see, this object is antisymmetric. You swap R1, R2, it changes sign. Okay? And I can write this object in a very evocative way. That is, I can write it as FR1, GR2, FR2, and GR1. And if I take the determinant of this matrix, I have the diagonal minus the anti-diagonal. So it's exactly what is written here. And you can generalize this to any number of electrons. That is, you can write what is called a Slater determinant. And so Hartree figured out that you shouldn't approximate your wave function for iron 10 to the 78 number as just a product of 26 functions, so 26,000 numbers, but you should write it as a product of those 26 minus a product of those 26 when you do one swap, plus a product when you do two swaps, and so on and so forth. So you have to write it as a determinant. The determinant is a property of linear algebra, is totally antisymmetric. So the informational content has not changed. You still need the 26,000 numbers, so you are good. But now your wave function has the right symmetry. Okay? And all of a sudden, Pauli principle comes up. You know that two electrons cannot be in the same quantum state. Being in the same quantum state means that two electrons have the same wave function. But if they have the same wave function, two columns of this determinant are the same. And if two columns in a determinant are the same, the determinant is 0. Okay. So this is Pauli principle in Hartree-Fock. In reality, Pauli principle is more general, but this is already very sort of evocative. And so, the only thing that changes now that we've learned the spin statistics connection is that you need to use a wave function that is not a product of single electron wave function, but is a determinant of single electron wave function. And then you still use the variational principle. You ask yourself what are the conditions that each one particle wave function needs to fill. And so they need to be such that the energy is minimum. And so again, you have 26 differential equations. And those are called the Hartree-Fock equation. Hartree in Cambridge discovered it, and the Fock in St. Petersburg, that probably by then had become Leningrad, also discovered it in 1927. So they go under the two names. The Hartree-Fock equation are a little bit more complicated than the Hartree. They have a lot of nice properties. I won't go into those, but really this is the bedrock of chemistry. If you take an insulin molecule, if you take a caffeine molecule, if you have seen Breaking Bad, you take any other molecule and you calculate its electronic states with Hartree-Fock, you start doing quite a good job. And so this was 1927. And from here, quantum chemistry took off, studying molecules with computational methods. And people thought at how you can do improvements of Hartree-Fock using perturbation theory. That is what is called Müller-Plesset, second order, third order, fourth order. They try to add different ideas on how you do your triumph wave function. They develop things called couple clusters. Really accurate. The best that you can do these days multi-reference configuration interaction solves the Schrödinger equation almost exactly, but the cost scale exponentially with the number of electrons. Okay, that means if you're able to study 7 electrons in a whatever 7 electron atom. So if oxygen is, this is very difficult. So if let's forget. Let's move on. So, but you might not be able to do 8. It's also a great level because it means that, you know, if you have a friend that is super wealthy and sits on top of the biggest supercomputer in the world, he can only study 1 more electron than you. So it's actually good. But so quantum chemistry can be incredibly accurate, but it can deal at very high accuracy with very small system. And we want to study silicon that has, you know, 1 bazillion of electrons. And so what we are going to find, what we are going to do is change a paradigm. And this was first tried again by Enrico Fermi together with his colleague Thomas. And it says, well, let's actually move away completely from the wave function, because the wave function in any case is such a complex object, and say, why can't we really find an expression for the energy of my water molecule that depends only on the charge density of the water molecule? So if n of r is the charge density, so at every point I have an average number of electrons, can I write a function or a functional of that charge density? And so he said, well, it's a bit complicated because I can do some electrostatics. So I can say the, you know, charge, the contribution from the nuclei is just electrostatic. So I do the integral of the charge density in that attractive potential. I can do electrostatic interaction of the charge density with itself. But what is really difficult in quantum mechanics is this quantum kinetic energy term, because that's the second derivative of the wave function. But once you take the charge density, so if the charge density is the square modulus of the wave function, you obliterate all the knowledge about the derivative. I mean, you can see it very simply if you have a wave function that is what we call a plane wave, exponential of I k dot r. So depending on what k is, you can have a very short wavelength or a very long wavelength. So the kinetic energy, the second derivative, the curvature of these things can go from 0 to infinity. But if I take the square modulus of this, this is equal to 1. So I've obliterated completely the information. Fermi was not someone that would stop at, you know, such small problem, and he had a brilliant idea, and he did introduce what is called the local density approximation. So he said, we have our water molecule here. This is what it is, you know. And what we want is to extract from this charge density the kinetic energy term. And what is said is, well, we look at it piece by piece, infinitesimal cube by infinitesimal cube. Here the density is 0, here it grows, and then it goes to 0 again. And it says each infinitesimal cube contributes to the quantum kinetic energy of my water molecule exactly how it would contribute if we were to take the quantum kinetic energy of the homogeneous non-interacting electron gas. So what is the homogeneous non-interacting electron gas? It's a physical system where the electrons don't feel each other. Okay, so they don't have electrical repulsion. The only thing that matters is the density. I can have 10 electrons per angstrom cube, or I can have 20 electrons or 1 electron. And so as a function of the density, I can have I can actually analytically calculate this kinetic energy. Maybe I should use n rather than rho. And it happens, that's really the Sommerfeld model. It goes as the power 5/3. And so this is exact for a, very non-physical system, non-interacting electrons, but it's a start. And so what Fermi did was saying, well, let's, wherever there is rho, there is an n. I mean, I used here a rho, I should have used n. But so we say for my water molecule, for my 10 electrons, we build an energy model that has a quantum kinetic energy term that is made in the local density approximation. So each infinitesimal cube d of r contributes n to the 5/3. And then there is an electrostatic interaction of this charge density with external potential, and there is an interacting repulsion, and there is a repulsion of the charge density with itself. So now this is a very simple functional of the charge density. You put, your external potential, that is just the 3 nuclei, where you want, and for that external potential, you minimize this object, you find the n of r. And then you keep moving things, you keep moving the nuclei, and you minimize at every time. But, it's not anymore 10 to the 78 or 26,000. Is just n to the r, so it's just 1,000 real numbers. So it's really easy, and it doesn't scale with the number of electrons. You double the number of electrons, n is still, a scalar field of the position. Okay, so Dirac made some suggestion to try and take into account the spin symmetry. I don't want to focus too much, but when they tried solving something, they solved here. This is a good example, the argon atom. What they found is a charge density profile that goes like this, and the Hartree-Fock was going like this. What do we learn? It's quite okay. It gets the right shape, but it completely misses the shell structure of the atoms, okay? What Hartree-Fock would give you, or what, if you solve the Schrödinger equation for the hydrogen, you knew that you have the 1s, the 2s, the 2p, and the 3s level. So didn't really work well in practice, but it was a very appealing idea of trying to find an expression for the energy as a function of the charge density. And that's where Walter Kohn comes into play. So he goes to Paris, meets up with his friend Pierre Hohenberg, and they start to think at this problem that is, can you do a quantum mechanical theory that doesn't deal with the wave function, but deals only with the charge density? And that's what they tried. And of course, what they gave as a name to this theory is a functional theory of the density. We write functional, as Fermi tried to do, of the density, but trying to do it in a more rigorous way. And so this is what goes on under density functional theory. And I think given the time, we have probably 5 minutes left. So I give you an intro, and then we continue tomorrow. So what Hohenberg and Kohn said was this. If I have the external potential, proton, proton, oxygen, and I have 10 electrons, my problem is completely determined. Those 10 electrons will find their ground state by minimizing the energy functional or getting to the lowest energy eigenstate of the Schrödinger equation. So I don't know what this solution is, but I know that if I tell you where these 3 nuclei are, and I tell you that I have 10 electrons, the problem is completely defined. So now at least in principle, so if I give a new Vx and capital N, if I were a magician, I would know what the ground state wave function is. I just need to solve the Schrödinger equation. Forget that I cannot solve it in practice, but at least in principle, I have everything that I need. And if I have the ground state wave function, I have all the ground state properties of my system, including the energy of the system. So at least conceptually, I can say that, say, the energy, the ground state energy, and every other ground state property depends in some mysterious way from the external potential and the number of electrons. What Kohn proved is what we call the first Hohenberg and Kohn theorem. That is, not only the external potential and the number of electrons determine the ground state energy, but they also determine all other properties, including the ground state charge density. So I say, these are the two protons, this is the electron. I know that if I have 10 electrons, those 10 electrons will do this croissant here. It was in France, so it was inspired. What he proved is the vice versa. This is incredibly important. It says, if someone gives me this croissant, if someone gives me a charge density, I know that I have 10 electrons. That's trivial. I just integrate the charge density. It doesn't require, it's not rocket science. But what Kohn says, if you give me this charge density, I also know that I have one proton here, and one oxygen nucleon here. So what is saying and is proving with that theorem is that there is a one-to-one correspondence between charge density and external potential plus number of electrons. So here I have external potential and number of electrons. So if I give you this through the Schrödinger equation, in principle, you can get the charge density. What Kohn proves is that if I give you the charge density, you integrate it, and very trivially, you know how many electrons you have, but you can also figure out that you have 2 protons and 1 oxygen nucleus. So there is a one-to-one correspondence. The proof will be on the slides. It's very simple, but I don't want to get distracted by this. What is really powerful is that now we can think not anymore a la Schrödinger, where we have an external potential and we need to find the wave function. So we don't start from the potential and the number of electrons as the fundamental variable, but because there is a one-to-one correspondence, we start from the charge density of the ground state. And we'll use that as a fundamental variable because at least in principle, if I have the ground state charge density, I would know what the external potential is. I would know what the total number of electrons is. I would know what the Schrödinger equation is. I would be able to solve the Schrödinger equation, and I would be able to get all the properties of the system. So this one-to-one correspondence means that from the ground state charge density, I can know everything that I want about my system. This is, you know, in all a series, you need not to give the solution. You need to sort of stop leaving the question, you know, how is it going to be? And to do this, we meet tomorrow again at 2 p.m. The good news is that there are a lot of croissants outside, so you can start thinking at the water molecule and so on. Is there any questions before we leave the room to our next group of people? Please.
So crystal field model potential is that in crystal field model, not in potential,
Yeah.
is that in this nucleus
Yeah.
part?
Yeah, it's exactly that. And then, you know, you might want to think that actually only the valence electrons are free to do what they are, And so you build the Madelung potential not just from the nuclei, but the nuclei plus the core electron. But this crystal field electrostatic is in the external potential. Cool, great. So we'll stop here, and we meet again tomorrow, and we'll post the lectures also on the Indico page.